Hello, Chase.
Hello?
How are you today?
Fairly good. I had to wake up early to go take a practice AP test.
The ACT or the AP?
I had to take a practice AP test for my history class.
For history, okay. Not the calc. Have you taken a practice AP calc test yet?
I have not taken a practice AP calc test yet.
When are you supposed to take your AP calc test?
I know that the AP calc test is, I think, May 7th.
Okay. I have a couple of them digitized into my computer. So whenever you feel the need to practice them, I have the material if you need it.
Okay, thank you.
This almost looks like it. No, this is going to be specific to 5.1 to 5.4. But let's go through this.
That's odd. Oh, I know what happened. Okay.
Is this not the right material?
No. It's the right material, but I don't use Microsoft Office. So on my computer, I had issues with the first question when I went to go do it, because it didn't give me infinity symbols since they don't exist.
Ah.
So I was trying to figure out what, I put it in chat, what that symbol meant to answer this question. So it makes, yeah.
So how are we going to solve this?
So finding the domain of the function f of x equals the natural log of 3x plus 1. The domain is the x values it could be, so then isn't that just anything that keeps that positive?
So we're going to set 3x plus 1 has to be greater than 0. Not greater than or equal to, but greater than 0. So x has to be greater than minus 1/3 b. And notice the difference between parentheses and brackets.
Yeah.
In other words, if the problem was this, what is the domain of that? It would be y has to be greater than or equal to negative 1/3, which would give it an answer that looked like that instead of the one we're looking at.
Yeah. That makes a whole lot more sense.
Yeah, brackets merely mean you can be equal or greater.
I originally had issues with this question because I opened it up and I saw those Y symbols and was trying to figure out how to solve this.
Yeah. All right. I always find it a bit curious that they don't use parentheses here.
So then, for this one, isn't it just C? Oh no, it has a Y, doesn't it? Oh yeah, C. Doesn't C work?
I think C does work. Hold on a second.
Because that's what I got to when I solved it.
Well, when I looked at this earlier, I got a different answer. I got A also. Why does A not work?
A doesn't work because you're breaking apart the 8 and the x, and you can't do that since it's multiplication, and we don't.
Yeah, you can. Yeah, no, you can. For sure. The natural log of 8x is equal to the natural log of 8 plus the natural log of x.
It's the addition we don't have the rule for.
Well, the division, that really should be in parentheses, and it should say natural log of 3 plus natural log of y in parentheses, and when you remove the parentheses, you get this. So, to me, A and C are the same, and in fact, why is E not correct?
E is not correct. Thank you, sir. E is not correct because I'm not sure why he's not correct. It's
I think
not all the way
made,
simple.
I think they made a mistake on this problem.
Yeah?
Uh-huh.
Look at it, they all do look fairly...
Yeah, they look... A is the same as C, is the same as E. The only one that's different is B, and only because they don't have a parentheses here.
Mm-hmm.
So I don't know what to make of this one.
So, oh, I guess I'll like A, C, and E all are...
Well, that's very peculiar. Why is it not B? Because you really need a parentheses. In other words, it could be the natural log of 8x squared minus the natural log of 3y. But then when you separate that, there's a parentheses, natural log of 3 plus natural log of y, and it doesn't end up being this when you remove the parentheses. So I don't know, that's a very strange one.
Yeah.
And it's not like that's even calculus. That's pre-algebra. I've done a lot of pre-algebra with logs. So, whenever we're asked to do derivative, let's automatically do this.
Yeah.
Get rid of the radical sign. Oops. 1/2, not 1/4. So what is y prime?
So,
Derivative of the outside times the derivative of the inside. So
then the derivative
Go ahead.
of the outside would be 1 over that, and then the derivative times the derivative of the inside, which would be 2x, instead of 2x on the top. So that would come to b.
Yeah. No.
No?
Hold on. For some reason, I didn't see this first time through. Let's examine this just a little bit more. So, when you're confused about outside and inside, the best thing to do is to use U substitution. Okay? Am I going to let U equal x squared plus 4, or am I going to let U equal x squared plus 4 to the 1/2?
X squared plus 4.
Alright. So, what is du? dx.
Oh, see, I can see where the problem lies. So
let's let it be x squared plus 4 to the 1/2.
Yeah.
Now we're going to take the natural log of u, which would be 1 over u times du dx. So let's figure out what du dx is here. It's equal to 1/2 x squared plus 4 to the minus 1/2 times the derivative of the inside, dx, 2x.
Yeah.
So my y prime has to be 1 over this times du dx, which is 1/2. This is in the denominator, x squared plus 4 to the 1/2, and the 2x is in the numerator. Now
Yeah.
the 2's cancel, and we have x over x squared plus 4. That should be on there as an answer. C.
Okay.
Yeah, you have to be a little careful there. There's actually 2 insides.
I see what I did then.
There's the inside of the square root function, and there's the inside of the natural log function. So you really have to apply the chain rule twice there.
That's tricky.
It is. I didn't see it the first time I looked at it. This is a little tricky also.
Yeah, I had issues with this one.
Yeah, I can see why. Let's separate that into 2 fractions. Well, first of all, there's 2 ways to do it. You could first of all take the derivative of each of these 4 answers and see if you get that, in which case that's the answer. And that's always the best way to do it if you can't figure out how to integrate it. A lot of these functions are extremely difficult to integrate. This one, I think I happen to know how to integrate it. Split it into 2 fractions. What's the first fraction?
X over x plus 1. And the second one would be 2 over x plus 1.
This one here is easy to integrate, right?
Yeah.
That's just 2 natural log of x plus 1. Okay. So the one that we're not sure about is this one here. But it turns out that this actually can be integrated using U substitution fairly easily. Let's do it. If U is equal to x plus 1. Now it doesn't look like a typical candidate for U substitution, because the derivative of this is not going to take away that. But I can now say that if U equals x plus 1, x equals U minus 1. It's just a change of variable. And du is equal to dx. So I have the integral of U minus 1 over U du. Now can you see that that is far easier to integrate than that?
Yeah, that is a lot.
Well, because this comes down to 1 minus 1 over u. Well, we know the integral of both of those. In other words, when we break this up into 2 fractions, we're going to have u plus natural log u. So, this basically is the same as that part because of this here. So let's solve that part here. So this is equal to the integral of 1 du minus the integral of 1 over u du, and plus this part over here, plus the integral of 1 over x plus 1 dx. Well, that gives us, the integral of 1 is what?
The integral of 1 is x.
In this case, u. Minus what? This one?
Minus, U over the natural log, yeah.
It's the natural log of u. Always remember that 1 over u is integrates to natural log.
U is natural, yeah.
Plus 2 times the natural log of x plus 1 plus c. Now, to get the whole thing back into a polynomial, because we let u equal x plus 1, so my answer is x plus 1 minus natural log of x plus 1 plus 2 natural log of x plus 1 plus c. Well, I can actually combine those two things. If I have a minus natural log and a plus 2 natural log, that combines to x plus 1 plus natural log of x plus 1 plus c. We should find that answer on there.
That explains why I had issues doing this first time. I didn't do that.
Well, I don't see quite that answer. I'm off by 1. Now, I suppose I can take this 1 and add it to my c to get their answer.
Yeah, I think that makes sense then, because C.
Yeah. But the real way to do it, to verify that this is the correct answer, D, is let's real quickly differentiate that. Well, 1 plus 1 over x plus 1. Now the question is that this? Well, if I find a common denominator and multiply the left side of this x plus 1 over x plus 1 to give it a common denominator, then I get x plus 1 over x plus 1, which is x plus 2 over x plus 1. So indeed, when you take the derivative of d, you do get this.
Although for this one, it looks like taking the derivative of those 4 answers may have been quicker.
Maybe. But this had a lot of key things in it that were useful to know. In other words, what did we learn here? First of all, we learned that if we split it into 2 fractions, we actually can take the integral of both fractions, even though we have to use the u substitution on the first fraction. And it's unusual u substitution. It is not typical. It's a change of variable u substitution. There's pretty much 2 types of u substitution. One where you have a composite function where the derivative of the inside is a product of your function. And the other kind of u substitution is where you just change the variable, like we did here. This demonstrated that. So I actually like this problem as a method of teaching integration. Of course, if you're taking a test and your sole goal is to get the answer, the problem is that when they stick none of these on there, that means that there's a possibility we're going to have to differentiate all 4 of these and be perfect about it. And if none of the 4 give us this answer, then we're going to choose this. But that's a lot of work. That may actually be more work than going through the process of integration.
Into the tangent of 3x dx.
First of all, let's figure out how to do that one.
The integral of tangent x?
Yeah. Because it's not 100% clear how to do this, and it's also useful to do this using u substitution.
to do this, wouldn't we then, yeah, make it into sine cosine, and then substitute the u for the cosine? Or
Yes.
cosine for...
And the u, incidentally, it does not work substituting it for sine. It only works substituting it for cosine because we know the derivative of cosine is going to end up in the denominator, and it'll take care of this sine x.
Yeah. Negative dx. And then substitute that in.
Well, notice I added a double negative.
Yeah.
The reason I did it is because I'm looking for that expression right there. And I now see it. That's du. In other words, that thing there is equal to du. I'm looking at that right there. That's equal to du. So I have a minus integral of du over u. Well, we know what that is. What is that?
Du over u is the natural log of u. Or the negative natural log of u.
The natural log, the negative natural log of cosine x when I go back into substitute.
Yeah.
So I know that the integral of the tangent is this. And it's almost worth memorizing that because you end up having to integrate tangent quite a bit. But it's also very useful to refresh on how to do u substitution, and this is perfect for u substitution. So now, what is the integral of tangent of 3x going to be?
Integral of tangent of 3x. See, I'm not sure what we do with the 3 now.
Well, let's look at some other situations. What's that equal to?
The integral of cosine. I'm not sure off the top. Isn't the integral of cosine sine?
Uh-huh.
Yeah.
Okay. So what's the
integral?
integral of cosine of 2x?
Is that just
The sine of 2x divided by 2.
by 2? So
In
then,
other words, you always divide it by the coefficient. Because if we take the derivative of that, we're going to get the cosine of 2x divided by 2 multiplied by the inside multiplied by 2. We get what we started with. So when you integrate a trig function, you get what you would have gotten if you integrate cosine of x divided by the coefficient of the angle. So since we're integrating tan of 3x, and we know tan of x is natural log, we know that the integral of tan x equals minus natural log of cosine x plus c. So it's not a huge stretch to integrate the tan of 3x is going to be minus 1/3 natural log of cosine of x plus c. And just to test it, let's differentiate that. Whoops. I need a 3x in there.
yeah.
Because I'm going to end up with 1 over cosine of 3x times the negative sine of 3x times 3. And that's going to get me back to sine of 3x over cosine of 3x, which is tangent of 3x.
Okay, that makes sense. I understand now. That was my original issue. Is I remember solving this one, and I got the negative ln cosine of x plus c, but I didn't know what to do with the 3.
Yeah.
So I wasn't sure.
Yeah, it looks very easily like it could be d But you always have to divide by the derivative of that inside term right there. And it's negative. In other words, tangent of x is negative log. So almost immediately, if we had to guess, we would guess A.
Yeah. Which... 2 to e to the plus.
So what is the integral of that?
2.
Just that.
So just the integral of 1 over x plus 1. Isn't that just the natural log of x minus 1?
Yeah, because the derivative of the inside is 1. So we don't need to worry about it. So we're just evaluating this from 2 to e plus 1. So this is actually very easy. So tell me what it is.
So the natural log of 2 minus 1 is...
Start at the
0.
top. Always start at the top.
So there we go. Natural log of... That turns into the natural log of e, doesn't that?
Okay. That's the top.
Minus the natural log of 1. Because you put the 2 in and you get 1. And then isn't the natural log of e 1, and then the natural log of 1 0? So you get 1.
Uh-huh. C.
So I had originally done that backwards because I didn't start at the top and I had put the 2 in, but luckily for this one I got the same thing since 2 turns into 0.
Oh, yes.
Because I did
Although
get
you
positive 1.
might have gotten the wrong sign. You might have gotten minus 1.
I don't know how I messed. I screwed something else up, obviously, but I did get C as the answer,
Okay.
even though I did it backwards.
In general, that is a hyperbolic function, meaning it's going to look something like this.
Yeah.
Is that going to be 1 to 1?
I don't think so.
1 to 1 means it has to pass the vertical line test, and it has to pass the horizontal line test.
Well, then yeah, that would be 1 to 1 if
It is 1 to 1. In other words, it's the same as y equals 1 over x, which looks exactly like that.
Yeah.
This just has an asymptote that moves to the left and a little bit of a vertical stretch, but it is 1 to 1. So the question is, how do we solve for its inverse? Really, really easy. I can't believe this question is on here.
Solving for the inverse is just...
There's 2 steps. Step 1 is you switch the variable.
Yeah, switch x, y, and then solve it for y again.
Step 2 is solve for y.
Yeah. So then here I would multiply both sides by y plus 2 to move it out of the denominator. X equals 7, and then divide by x to move the x over, and then subtract 2.
That's what we're looking for.
And that would be none of those.
Look closely. For some reason, not quite sure, but an awful lot of people have trouble with this.
Is it C?
7 over x minus 2.
Oh.
They have trouble with that because they do not think of a common denominator.
Oh.
And you need to.
Yeah.
In other words, this is f inverse, what I came up with.
Yeah.
But when I present this kind of a problem to most people, they have difficulty with it, even calculus students.
Yeah.
They don't think that, I don't know why, it's like a block, a brain block. They don't seem to realize that the common denominator is x, which means this has to be that. And then you act on the numerators, you maintain your common denominator, and you get c.
Yeah.
Okay? Another one that looks like it has a double inside.
E cotangent of x squared.
In other words, this would be a single inside, where u would be cotangent of x. Here, u is going to be cotangent of x squared. So there's either two ways to do it. You can actually go through the u substitution, or you can recognize that it's just a double inside, and we're always going to take the derivative of the outside times the derivative of the inside times the derivative of the inside. So what's the derivative of the outside?
Cotangent x squared times e to the...
No, the derivative of e to the u is e to the u.
To the u, yeah.
So it's e to the cotangent x squared. That's the derivative of the outside.
And then we want to do the derivative of cotangent x squared.
Well, and then the derivative of x squared. So what's the derivative of cotangent of x squared?
The derivative of cotangent of x squared.
Remember the derivative of tangent.
The derivative of tangent is 1 over x, right?
It's secant squared.
Oh. Well,
so the derivative of cotangent, because it's the cofunction, is minus the cofunction of that squared.
And then...
So the derivative of cotangent of x squared is
negative
minus cosecant of x squared. And then we have one more inside that we haven't applied.
Yeah.
2x.
And then that should be one of the answers.
Well, let's see. Hold on here. Here's our e to the cotangent x squared. There's our negative cosecant of x squared. There's no 2x there. This is the same answer with a 2x. So it's C. Notice that they always write it backwards. In other words, when you do the derivative, they always teach you to take the derivative of the outside times the derivative of the inside times the derivative of the inside. That's always going to give you this. And yet, when they put their answer up, they start with the 2x, and then the cosecant of x squared, and then e to the cotangent of x squared. Only one problem here. They got the cosecant squared. Oh, that's what it is. I made a mistake when I wrote it. Yeah, no, the derivative of cotangent of x squared is cosecant squared of x squared. Here, I made that mistake. Let's go through it. If y equal cotangent of x squared, then y prime equals negative cosecant squared of x squared times 2x. In other words, the derivative of cotangent is negative cosecant squared.
Yeah.
All right. Well, this is nice.
To the end. Nice.
Now, before we resort to our solution of last resort, and notice they make every one of these tough by putting in a none of these, which means you might have to differentiate all four of these and still not get an answer. Before we do that, let's see if there isn't a different method we can use. Let's see, if I let u equal square root of x, then I'm going to have the integral of e to the u all over u. That doesn't work. Or does it? No. Let's see. What if I let u equal e to the square root of x, then the natural log of u would equal square root of x, and I would have the integral of u over natural log of u. That still doesn't work.
This one's it's a lovely question.
E to the x over... Have you learned integration by parts?
Integration by parts.
Probably not.
I don't.
It's where you log poet or lip it. In other words, a typical integration by parts would be try to integrate that. Only way to integrate that is by parts. You and I haven't covered integration by parts. I'm quite certain. So I'm guessing you haven't had it.
I mean, look real quick. I don't think we have
You'd remember it. You'd remember it if you had it. It ends up being uv minus the integral of v du. So if you don't recognize that, you haven't had it.
No, we haven't. Looking through here.
All right. Let me study this for just a second more. Can I integrate this? I don't think I can integrate that. What would the integral be? Well, let's take a different approach. Let's start differentiating these. These don't look that hard to differentiate. What's the derivative of this?
Since the derivative of e to the x is e to the x, isn't that just e to the...
It's 2 e to the x to the 1/2 times the derivative of the inside, which is 1/2 x to the minus 1/2. The 2's cancel. We have e to the x the square root of x all over the square root of x. Is that what we started with? Yes.
Yeah.
So I feel like I almost cheated, but that works. And perhaps that's the reason they made 1 the correct answer, is because I'm not sure that you have a method for integrating that, which means the only method you have for solving this is to start differentiating each one. And they made it easy for you by making the first one work.
Mm-hmm. That's nice. Good strategy to remember. You can't figure out how to integrate it, just that's like really good.
Yeah, there probably is a way to integrate that, and I'm just overlooking it. I don't know. Integration is a tough thing. It's real easy to forget how to integrate by a certain technique. Make up your own integration problem involving the natural exponential function and use substitution, then solve your problem.
So, make up your own using U substitution. I think you have to have one that would work with U substitution. Even 3x dx.
What would U be?
Would U be the 3x?
So du is equal to 3dx. So if I multiply this by 1/3 and multiply it by 3, there's my 3dx. So now this whole thing is equal to 1/3 e to the u, excuse me, 1/3 of 3 e to the u, which equals e to the u, or e to the 3x.
So, this number 10 really isn't as hard as it makes itself seem to be.
Not at all. In other words, it's exactly what I did.
Yeah.
Let's integrate e to some variable other than just x. No matter what I put in here, I'm going to use u substitution. I'm just going to let u be equal to that. But it's worth knowing that that is always e to the 3x divided by 3. Same way that the integral of cosine of 5x is sine to the 5x divided by 5. These transcendental functions are like that, where you don't have to actually use u substitution if you recognize that it's just that divided by the coefficient.
Oh, so that question really was a whole lot harder than when I first was, or a whole lot easier than
Yeah,
when I first read it.
you could, well, there are some functions, like this one, that,
Yeah.
guess what? That doesn't have an antiderivative. Not in all of math. There is no function whose derivative is equal to that. So the only way to integrate this kind of a function is by approximating it with infinite series, which you won't get until Calc BC. That's the C part of Calc BC.
The infinite series.
Where we let e to the x be approximated by the polynomial you can actually approximate e to the x by this polynomial. In other words, if you want to know what e squared is, just put in 2 for x, figure out some number of terms. This is actually an infinite series that goes on and on forever like this. But if you use like the first 3 or 4 terms of it, you'll get an excellent approximation for e. If I want e to the 1, well, I know that's 2.71. Well, in this case, it's 1 plus 1 plus 1/2 plus 1 over 6. This is 2 factorial and 3 factorial. And you can see that that is honing right in on 2.7. And the more terms you add, the closer you'll get.
That's pretty cool.
It is pretty cool. It's what infinite series is all about, is it's taking a standard polynomial function and representing it by an infinite polynomial series. The beauty is that when you go to integrate this, I can't integrate that, but I can integrate term by term of that. So all I have to do is plug in minus x squared wherever I see x and integrate that polynomial. And then I have the integral of that. So just so you know, there are lots of functions that do not have antiderivatives, and that in a way is what makes calculus so hard.
Is knowing what does and what doesn't.
Well,
I think that's the last question.
Yeah, it is. Well, notice that differential calculus, it does not matter how complicated the function is. I can put 3 different functions in the numerator and 4 different functions in the denominator, and you can still differentiate it using only the power rule, the quotient rule, the product rule, and the chain rule. Not the same with integral calculus. There's all kinds of functions you can't integrate easily, or with a special rule, or any of that. That's why I said, have you had integration by parts? Because that's a whole nother technique for integrating the product of 2 functions. You know, the product of x times sine x. You have no way of integrating that right now.
Nope.
But with integration by parts, we do have a way of integrating that. And then there's integration by partial fractions. If I want to integrate this, I have to break it into 2 partial fractions, and the beauty is that you can integrate the sum of 2 things by taking the sum of the integral. But you can't integrate the product of 2 things very easily.
Yeah.
So this requires partial fractions. And then there's another technique where you use inverse trig functions. And then there's another technique where you use trig substitution. So there's more techniques yet that you still have to learn than you've learned already for integration. And each one of them gets kind of progressively harder.
So integration is just a matter of knowing all these different ways that might work on your phone.
Yeah, pretty much. Pretty much.
On occasion you don't.
Well, it's hard. I mean, there's certain, I haven't tried to integrate all functions, but I know that each time you learn a technique of integration, you get given a certain type function that's going to work with that technique. So I really don't have any idea what percentage of the functions you run into in the real world can be integrated with the techniques that we know.
Yeah.
Or do they need approximation techniques? That integral of e to the minus x squared is actually an approximation technique, because I can say that's equal to an infinite series, but I can't integrate every term of an infinite series. But I can integrate the first 5 terms, and the first 5 terms are going to give you an accuracy to within 1 billionth. That's how good infinite series are for approximating functions. And in fact, it's infinite series that allows us to calculate pi to any number of places that we want. Haven't you ever wondered how they calculate it to 25,000 places? they certainly don't take a circle and divide it by its diameter and try to measure it that accurately. They do it.
Yeah,
They do it using infinite series, believe it or not. And
I just assumed that they were dividing a circle by its diameter, but
I always
when I
did
think
too.
about it,
I always
that
did too, and I
ridiculous.
never could figure out how they could get it accurately to 25,000 places that way.
Because that seems a little ridiculous.
Uh-huh. Well, it's a little ridiculous to calculate it to 25,000 places, since 9 places are all you need. The difference between 9 places and 10 places is the length of a football in the width of the universe. In other words, if you were to measure the volume of the universe using its radius, and you use pi to 9 places, it's going to be accurate to within the length of a football. So there's no real need to ever need pi to any more places than 9 or 10. It's just an exercise in mathematics, but the way they do it is with infinite series.
It's pretty cool.
Yeah, actually infinite series are pretty cool. Very, very hard. It'll be the hardest part of calculus by the time you get there. But I understand. All right.
That's all I have for today.
Okay, if that's all you have, let's call it a day.
Thank you.
I will talk to you next Saturday, Chase.
Talk to you next Saturday.
Bye-bye.